So thank you. So my talk today, I'm Hui Yang, and my talk today is about the biomass change from the L-band VOD. I did this work with Philip and Jean-Pierre when I was in LCE. So in this work, we try to use the small L-band VOD data to map the biomass changes. The LVOD are measured every 1 to 3 days and at both ascending and descending orbits. And its spatial resolution is about 25 kilometers. So it's quite coarse resolution. We don't find obvious situations in this this data and in the dense forest region. And compared to the X-band and the C-band, the L-band sensors can monitor deeper and can give more information about changes in stems and the branches. And I know there are quite different opinions towards the VOD. So the VOD do have some limitations, like its signal disturbance from the radio frequency interference in the northern populated regions. So that's why the earlier LVOD data only focus on the tropical region. The second, the VOD is not only sensitive to the biomass change, it's also sensitive to the vegetation water content change. So if directly regarding the VOD as biomass can have large bells. So in this analysis, we try to design a new filtering method to remove the alpha effect and to remove the water content effect. The first step is as shown in this workflow, we did the filtering to LVOD 3 times. First use a loose filtering method and then use a strict rules to filter. And we also compare the ascending and descending data. We think the value of ascending and descending measured at the same day should be similar. If they are not, we will remove the bad quality one. And after filtering, we only keep the very good quality data and we do reconstruct. We use the method which were used to reconstruct CO2 measurements by the NOVA, that is feed the data and reconstruct the long-term change and the seasonality change. And then we extract the signal according the frequency of the time, the data, time series, and using the Fourier transform. After that, we can have a reconstructed LVOD data, which have different time scale variability, like long-term change and seasonality change. Then we use the spatial relationship between LVOD and the biomass to get the annual biomass map. In this work, we only keep the signal of the long-term changes to remove the water content effect. And we also calculate the annual value, only use the LVOD in wet seasons because we think water in wet season are saturated. So the year-to-year changes in VOD are mainly reflect the biomass change rather than the water content changes. This is the map we finally got. It's the biomass changes from the 2010 and 2019. And globally, we found the carbon stock increase at a rate of 0.5 petagram carbons per year. And the boreal region and the temperate region are the largest and second largest contributor to this carbon sink. The wet tropics and the arid region act as carbon source. And we found this spatially, the patterns of biomass change are quite consistent with the forest coverage change from the global forest change database, like the forest loss and the biomass loss and the forest loss in the southwest Amazon and in the central Congo, in the Siberia and the North Europe region, and the biomass increase and the forest increase in the Southeast Asia and in the Eastern Europe and in the Canada. And then we use this classification map from the Curtis, this is the driver to the forest coverage change, and they divided the global into 6 clusters, including deforestation, agriculture, forestry, fire, urbanization, and non-forest loss. We calculate the biomass change for each of these clusters and get this figure. We found in the wet tropics and the dry tropics, the carbon loss are mainly from the region with deforestation and agricultural disturbances. And in the temperate and the boreal region, the forest increase are from the region of the forestry and the non-forest loss. And that next is we want to compare our estimates with the global carbon project estimates. So the residual of the fossil fuel and the fossil fuel emission, CO2 growth rate, and the ocean sink should remove the lateral riverine flux and remove the carbon for crop and the wood productivity, and then can compared with our estimates. This is 0.9 petagram carbon per year. It's close to our estimates, but still have 0.4 differences. So to explain the soil organic carbon changes can partly explain these differences, but we don't exactly know how many soil carbon organic changes because we don't have observation-based estimates, and the model estimates for this part have very large spread. It's changing from minus 0.1 to 3 petagram carbons. And the last thing I want to show is we compared our results with the DGVM outputs, and we found the models predict quite different biomass change, like model predict the carbon sink in the wet tropics and the carbon source in the dry tropics, and the smaller carbon sink in the temperate region. And there are a lot of possible reasons to explain this, like in temperate region, model don't consider the plantation signal. This is the land use forcing for model. We see in South China, the forest coverage are decreased, but from the satellite data, we see clear significant increase in LAI and in forest coverage in this region. And for the tropical region, model don't consider the forest degradation, don't consider the small fires effects, and don't consider the fossil fuel limitation to growth. But except all this possible reason, we think there another more important reason is model don't include the forest age informations. We think the young forest and old forest should have different capacity to uptake and to release carbon, but model don't consider this. And we use forest age map to calculate the average biomass change for the young forest and to the old forest. And we found in VOD data, young forest and the middle forest dominate the carbon sink. And the old forest are approximately the carbon neutral carbon source, but the models predict inverse patterns of the biomass changes. It could due to model don't consider the secondary forest regrowth and after the disturbance, or it's overestimated the old growth forest metabolic activity. So for this work, we developed a new method to remove the R5 effect, to remove the water content effect on LVOD and generate a global coverage map of biomass change from LVOD. And globally, we found the carbon stock from 2010 increase 0.5 petagram carbon per year. And boreal and temperate region are the major contributors, the wet tropical carbon source. And we think our results show the young and middle-aged forests are major contributors to the carbon sink.